a hard curve sketch. Can't see that at all. What's going on here? Oh, there it is. Off the top of my, I don't know what's going on. That's all right. Let's do a hard curve sketching. Well, my view is kind of misaligned somehow. I'll try and keep it inside the box. Here it is. F of x equals 6x to the 2/3 minus 4x. All right. It's that 2/3 power there, which is going to make some parts of this come out kind of weird. But let's not worry about it so much. Let's just do the standard, the same old procedure. Remember, the procedure is you make the chart of the increasings and decreasings, and you also make the chart of the concave ups and downs. That uses the second derivative. And then you kind of try and piece everything together and draw your picture. So first of all, the increasing, decreasing. We begin by taking the derivative, finding the critical numbers. So I'm going to go f prime of x. This is not so hard. You go x to the 2/3. So the 6 gets multiplied by 2/3. I get 4. And then x, what's the new exponent going to be? You subtract 1. Negative 1/3, yeah. You subtract 1. Okay, and then minus 4x just turns into minus 4. That's easy enough. All right. I suppose you could factor the 4 here. It's not a big deal. Then it's just x to the minus 1/3 minus 1. And just for the sake of, I'm going to set this equal to 0 and try and solve all that business. I'm going to write this again as a fraction. It is a negative exponent, right? X to the minus 1/3. That's the same as 1 divided by x to the 1/3. And x to the 1/3, I'm going to write as cube root of x, because that's what it is. Like so. All right? And then minus 1, of course. Okay, this is the derivative, f prime of x. What we got to do, we got to find the critical numbers means set this equal to 0 and solve. And then also say when this does not exist. Maybe I'll just do the DNE part because that's easier. Do you see any value of x which makes this not exist? You should be looking for zeros in the denominator. What do you think? Any value of x makes the denominator 0? Actually, you can have negative numbers inside a cube root. You can't inside a square root, but yeah, it's not a big deal. The negatives doesn't matter. 0 in the denominator is the problem, though. What x value gives you 0 in the denominator? 0. Yeah, some people are giving me the signal. It's 0. Yeah, if x is 0, then this looks like 1 divided by 0. That's not allowed. So here, I'll just say the denominator. In this step, you set denominators equal to 0. Wherever you see a denominator, well, there's only one spot here. It's cube root x equals 0, which means x equals 0. Okay, so that's going to be one of my critical numbers. And then what else? I also need to say when f prime equals 0. So, all right. This is a little more work, but not so bad. 1 over cube root x minus 1. Like that, right? We set the whole first derivative equal to 0 and solve for x. How would I solve for x? I would say, first of all, let's just divide both sides by 4. The 4 will just disappear because it's a 0 on the other side. 1 over cube root x minus 1 equals 0. How about add the 1? 1 over cube root x equals 1. What would I do to solve for x here? Remember your algebra of your youth? What did you do there? Yeah, that denominator there, I want to multiply it on both sides. So on the left side, it will end up just being 1, and on the right side, it'll be cube root of x. And then I could, I guess, cube on both sides. Gives me 1 equals x. All right? So this is my other critical number. We have two critical numbers. I circled one and I put a box in the other. That means nothing. I should have been more consistent with my circling and boxing. All right? Okay, I'm going to make that little chart about when it's increasing versus decreasing. Those two numbers go on the chart. So 0, 1. And I'm going to choose other numbers in between and plug them into the first derivative, which is right here, right? Just barely at the top there. Sorry, my screen is somehow zoomed in. It's not fitting as well. All right. So let's plug some numbers. Here, I'll bring this down here so we can see it. We're going to plug into that. On the left side, say less than 0, I'll choose -1. So f prime of -1 is 4. 1 over cube root -1, -1. Cube root of -1 is -1. That's because -1 times itself 3 times equals -1. So this is just 1 over -1 and then -1. That's 4 times -2 there. -8, which is negative, so I'll put a minus sign there. I will refresh my memory. The first derivative there, it does not exist at the 0, and it equals 0 at the 1. All right. Okay, what number should I choose between 0 and 1? Or how about let's choose to the right of 1. What's your favorite number over here to plug into this function? Two. Yeah, I expected everybody to say 2. Actually, I'm not going to choose 2. Why I'm not going to choose 2 is because actually I'm going to have to plug it into here, and I don't really like to do cube root of 2, without a calculator. Anybody have another non-standard choice? 8. Yeah, I'm going to choose 8. So this is a little life hack. The number, you want to choose the number, choose a convenient number to plug into that function. Usually, with a polynomial, it doesn't really matter. But with that weird cube root in there, I'm going to choose 8. So it's going to be 4. 1 over cube root 8 minus 1. Cube root 8, of course, is 2. So this is 4. 1 over 2 minus 1. So that's 4 times negative a half. This is positive and that's negative. So it's negative over there. And then in the middle, can we be cute about this one too? Is there any number that you like to take the cube root of between 0 and 1? Ordinarily I would choose a half, but I don't like cube root of a half. Any thoughts? Is there any cube root number in there you do like the cube root of? No? 0.8? No. That's a good idea, but decimals don't work well with square roots. Like you can't do, or definitely not with cube roots. Any other ideas? 0.8 is kind of a good idea. I'm going to choose, how about 1/8. How about that? 1/8 you can find the cube root of. The cube root of 1/8 is 1/2, isn't it? I think it is. F of 1/8. One moment here. My dear wife is texting me. It's popping up on the screen there. 1/8. All right. 1 over cube root of 1/8. This is some tricky little tricks. What? Did you see me? I just put on the moon, and the text still comes. Maybe I don't understand how the moon works. I'm thinking about going to airplane mode, but I'm concerned that will ruin I'm using the wire here. I don't want to risk it. I would just ignore the texts. The alternative is I could have ignored the text all along and not mentioned it to you all, because you don't care, But I like mentioning things from time to time. It's like that, right? Cube root of 1/8 is 1/2. It's in the denominator, so that 1 over 1/2 is actually a 2. So there's 2 minus 1 there. This is 4 times 2 minus 1, which is positive. So in the middle, it's a positive, all right? So this was supposed to be a harder one, remember? That was a somewhat tricky plugging in, although if you're using a calculator for this, it really wouldn't matter. You could plug whatever numbers you like in there to see if they're positive or negative. One thing that's interesting about this function is this dne right here. We have a point here where the derivative does not exist, but this is at x equals 0. In the original function, you will notice, actually this original function does exist when x equals 0. So this is not a dne because it's an asymptote, which we have seen that before. This is actually a dne because the graph really does exist. It just has like a pointy point at x equals 0. So this is weird. We'll see that eventually when we draw the picture. Anyway, this is the chart for the increasing, decreasing. We're going to do the same thing for the concave up versus concave down. So in order to do that, I'm going to find the second derivative, and all of these different versions here are different versions of the first derivative. We need to take the derivative again. I think the very first one is the most convenient when it comes to taking the derivative again. So I'm going to start there, and then take the derivative again. Down here. So that's the first derivative. The second derivative is multiply the negative 1/3 down, I get negative 4/3, x to the minus 4/3. And then the 4 just goes away because it's a constant. This is actually a little simpler this time. Writing it as a fraction again is negative 4/3 times 1 over x to the 4/3. All right? And again, I got to say when this equals 0 and also when this does not exist. The dne part, again, we will get x equals 0 because if I put x equals 0 in the denominator, that makes it 0 in the denominator. So I'm going to say f double prime does not exist is x equals 0 because that makes the denominator 0. The f double prime equals 1, we have to do some work for that. We set the second derivative equals 1. What? Equal to 0. Sorry, I don't know why I said that. The second derivative equals 0. 1 over x to the 4/3 equals 0, like that. And now I'm going to try to solve this for x. I could just divide the 4/3 onto the other side, and it will go away entirely because it's just a 0 on the other side. So this will say 1 over x to the 4/3 equals 0. Right? That coefficient of 4/3, you can just divide it out of the equation entirely. What should I do at this point? Well, at this point, when we did this a few minutes ago, somebody said, multiply that denominator onto the other side. So if I do that, it says 1 equals x to the 4/3 times 0. I multiply both sides by x to the 4/3, which I guess means 1 equals 0. What does that mean? 1 does not equal 0. So what's your interpretation of all of this? Yeah? Doesn't what? Yes, it means the second derivative never equals 0, right? It's so, like, this is never true for any value of x. That means this can never be true, which means this can never be true, which means this can never be true. So this step here where we set the second derivative equals 0, we just don't get any other critical numbers. So they're not critical numbers, they're second derivative. So this, I'm going to say, no solutions. So what that means is f double prime never equals 0, right? And so we don't get any extra numbers from that step. The only number we're going to put on our chart is this one, x equals 0. All right, so I'm going to make my chart of the second derivative signs with x equals 0 marked as a special point. Let's do it. X equals 0. All right, 0 is where the second derivative does not exist, so I'll put a little dne. And then we got to plug in on one side and on the other side. And I'm going to use this. I'll bring down the equation again. This is the second derivative right here. That's what I'm plugging into. So let's, you don't have to be too cute about this because I can just use 1 and -1 and then the powers work out nicely. So on the left side, I will use -1. It's going to say negative 4/3 times 1 over negative 1 to the 4/3. Remember that 4/3 power down there means do the 4th power and then take the cube root, or do the cube root and then take the 4th power. It's either way. How about, I'll think about do the 4th power first. That turns the -1 into a +1, and then you do the cube root of +1, which is +1. So that denominator there ends up being +1. So this is negative 4/3 times 1 over 1, which is negative. So the sign on the left is negative. All right, and then on the right side, I am using +1, negative 4/3 times 1 over 1 to the 4/3. That's just 1 in the bottom there, so this is negative 4/3, and so that's negative also. And that's the end of that chart. All right, how we doing so far? This was the hard part, I guess. The rest is just plugging in a bunch of values, which are easy in this problem, and then draw the picture. All right, let's see if we can finish it off. We are going to plot everything. We start with y values for the critical numbers and the second derivative points. They were, I'm going to plot x equals 0 and x equal 1, right? X equal 1 was a critical number. And, well, x equals 0 also, right? They were the two critical numbers. From the second derivative, we also had 0 there. So plotting x equals 0, x equal 1. So I need to find their y values, and I have to use the original formula. Look all the way back up to the very top, right? This guy. I'm plugging in 0 and 1 to this. This is pretty easy, right? When I plug in 0, I just get 0 everywhere there. 6 times 0 to the 2/3 minus 4 times 0. That's all 0. And then when I plug in 1, we get 6 times 1 to the 2/3 minus 4 times 1. That's 6 minus 4, which is 2. All right, so those are two special points that I'm going to put on the graph. I might as well start drawing the graph. The 2 points I have are, I scrolled it out, 0 and 0 is 1 point. That's here. And then x equal 1, y equals 2. Whoa. X equal 1, y equals 2. I'll put over here. 1 and all right. And if you recall, x equals 1 is where the derivative equals 0. If you look back at that first chart we had, x equals 1 is where the derivative equals 0. X equals 2 is where the derivative does not exist. So I'm going to put a little sort of flat liner right there, like I usually do. That means when I eventually draw the curve, it's going to go flat through that point. And this other point, I don't really know what it's going to look like, but it's going to be a pointy point, right? The derivative does not exist right there. So just to remind myself, this is going to be some kind of pointy, all right? And now we just draw the curves in according to the charts. I will try to summarize the charts that we had. Our first derivative chart, the f prime, was 0 and 1, and it was minus, plus, minus, I believe. With a dne here and a 0 here. And then our second derivative chart was just the 0 and a minus both times, and a dne. All right, so how do we draw those curves in? To the left of 0, to the left of the origin, it is decreasing and concave down. That means it's the frowny shape, but the decreasing part. So it goes like that, right? That's the shape of a decreasing concave down. All right. To the right of that point, just continuing to the right, between 0 and 1, look at the charts here. I have increasing concave down. So that means it's the frowny shape, but the increasing portion of it. That means it looks like that. And there you see the pointy point, all right? Ordinarily, if you see a point like that appearing in your graph, you probably mess something up, but it's correct in this example because this is a point where the derivative does not exist. This usually doesn't happen, but sometimes it does, all right? And then continuing on to the right, greater than 1, I want to see decreasing and concave down. That means the frowny shape and the part which is going down. So that just does that. There you go. This is the graph of that function. That's how we do it. Any thoughts about that? Questions about it? All right. Excellent. I hope you are satisfied with this slightly harder curve sketching. The pointy point is kind of cute, I think. All right. That's all I want to do for curve sketching, at least for now. Actually, we're going to come back to curve sketching for slightly more complicated functions. Really, all we did were polynomials, and then this one was like a polynomial that had some weird fractional exponent in it. We're going to come back and talk about sketching functions which have asymptotes, which none of our examples did that yet. So that's something to look forward to. What I would like to discuss today, our remaining time today, is something actually, to be honest, this I accidentally got out of order in my papers. I meant to talk about this before the curve sketching, although they have nothing to do with each other really, so you could do it any old way. But I want to talk about something called the second derivative test. It would be traditional to discuss the second derivative test immediately after discussing the first derivative test. For reasons unknown, I didn't do it that way. I meant to. I mixed it up. The second derivative test is an alternative to the first derivative test. So this is another way to identify a local minimum or maximum. The first derivative test was the first way that we learned to identify a local minimum or maximum. And I will sort of put this I'll write this inside a bracket here. I will refresh your memory about the first derivative test, because the second derivative test is meant to do the same thing. It's just a different method for doing the same thing. The first derivative test is so let me just label this. First derivative test. And the whole point of this and the second, they're both doing the same thing. The point of it is to tell if it's minimum versus a maximum. All right. First of all, you find the critical numbers, because that's how you find the point itself in the first place. Find the critical numbers, and then make the increasing, decreasing chart. And it looks something like, I'm just making this up, but you get something like this, maybe a plus, a minus, a plus, that thing. But using the first derivative, right? This is the increasing versus decreasing chart. And then, anybody remember the rule for this? Like this 2 here, according to this chart, is that 2 a maximum or a minimum? Yeah? It's a maximum. Yeah, why is that? Yeah, right. So this is the first derivative test. How you tell if it's maximum or minimum, you make this chart using the first derivative. And if it goes plus and then minus, that means this is a maximum. And if it goes minus and then plus, that means this is a minimum. That concept is called the first derivative test. All right? The second derivative test is meant to answer the same question. It tells you whether it's going to be a maximum or a minimum, but it's a little nicer in some sense because you don't have to do this chart. All right? So the second derivative test, I will say answers the same question. Is it a maximum versus is it a minimum? But you don't have to make that big chart. It's actually a little bit less work in the end. You have to do a little bit more work sometimes. It's really more a matter of when you encounter a new question like this, for certain types of problems, it's easier to do the second derivative test. For other types, you might be better off with the first derivative. Anyway, the second derivative test answers the same question, but requires no chart. That's what makes it better. What makes it a little worse is you have to use the second derivative. So you have to find what the second derivative of. you have to find what the second derivative is, which you never had to do in this problem. So it's a little bit more work in one sense, a little bit less work. For certain functions, if it's easy to find the second derivative, you might as well use the second derivative test. If it's a pain to find the second derivative, you might as well stop with the first derivative and then just do the first derivative test. All right. Anyway, how does it work? It's based on a very simple idea, and that is, remember, f double prime positive means this kind of shape. It means that you're looking at the smiley shape, right? And if the second derivative is negative, it means you're looking at the frowny shape this way. And so, if you have a point and you don't know if it's a minimum or a maximum, one way you could decide if it's a minimum or a maximum, really it's a matter of deciding, is it this kind of shape or is it this kind of shape? And you can just use the second derivative to determine that. So I'm going to write this like a theorem. It's not a very fancy idea, though. And this is called the second derivative test. This is telling you how to tell the difference between a minimum and a maximum. All right, it says if, well, let me say it this way, sorry. I'll just say let C be a critical number. That means either f prime equals 0 or f prime does not exist. If f double prime of C is positive, then, so what you do is you just take your critical number and you plug it directly into the second derivative. And then if that answer is positive, well, that means that the picture must look like this, right? And that means that your number must be the minimum because it's at the bottom of one of these smileys. Okay, so if the second derivative is positive, then C is a local minimum, right? This might seem backwards to you. I don't know. That's just the way it is, though. If the second derivative is positive, it's a minimum, and if the second derivative is negative, it's a maximum. Then C is a local maximum. Why that's true? It's because if the second derivative is negative, it means your shape looks like this, which means your point is actually the top of the hill. So it's a maximum. All right? This is the second derivative test. And I got to say, this does not include the situation when it's 0, right? I said when it's positive, it's a minimum. When it's negative, it's a maximum. What if it's 0? This is the bad news about the second derivative test. If f double prime of C equals 0 or does not exist, f double prime of C does not exist, then, unfortunately, we don't know. If this happens, this is like the worst case scenario. It means the second derivative test doesn't actually tell you anything about whether it's a minimum or a maximum. What are you going to do in that situation? Then you have to just use the first derivative test. There is no failure possibility for the first derivative test. So the second derivative test, in some rare cases, it might just not work at all. And in those cases, then we must use the first derivative test. Right? That's how it is, unfortunately. Let's try some examples. I would like to use the second derivative test to find the local extrema, that means minimum, maximum points, right? How about, let's use the second derivative test to find the local extrema for this here function. F of x equals 4x cubed plus 7x squared minus 10x plus 8. All right? Remember, the first derivative test and the second derivative test are just two different methods for answering the same question. So if I asked you on the test, say, like on one of our exams, just find the local extrema, then it would be up to you to do it either way around, whichever way you like. Although, I might ask it like this, just to force you to do it one way or the other way. You should know how to do it both ways. All right, find the local extrema for this. So what we do is, first of all, we find the critical numbers. The critical numbers, remember, are where the first derivative equals 0 or the first derivative does not exist. So I got to go f prime of x. Take the derivative here. It's going to be 12x squared plus 14x minus 10. And to find the critical numbers, you set the first derivative equal to 0, right? And also you say when the first derivative does not exist. So f prime equals 0. I say 12x squared plus 14x minus 10 equals 0. We're going to factor this to solve for x. I don't like that 12 in the front. But actually, you can't fully factor that 12 out. I think the best you can do is divide out a 2. 6x squared plus 7x minus 5. Yeah, it's not possible to take out any more constants. So we're going to have to do one of these slightly hard factorings. I don't know what kind of methods you know for doing factoring when there's a coefficient on the front, but I hope you know some kind of method. My method that I learned is just kind of like guess and check. Like these two numbers, so it's going to be something x plus something, and then something x plus something. They might be minus somethings, one of those. These two numbers here have to multiply to be 5, and these two numbers here have to multiply to be 6. Now there's a few different alternatives for what can be 6, but to multiply up to be 5, it has to be a 5 and a 1, right? So maybe I'll start by putting a 1 and a 5 here. One of those will be positive, the other will be negative. And then I have to stick coefficients in front of these x's so that when I multiply it all, do the FOIL thing, I end up with 7 in the middle. How can you end up with 7 in the middle? The answer is I just sort of guess. I mean, I could go a 1 here and a 6 here, or a 2 here and a 3 here, or it could go the other way around, a 3 and a 2, or a 6 and a 1. Anybody see how to do it? For example, if I were to choose the 6 and the 1, like that and like that, this is not correct because on the inside it adds up to 1, on the outside it adds up to 30. And that's not going to make 7 if you add those together, right? Can you possibly make 7 from any combination of these? The hardest part is the factoring. How about, I think I can do 2 here and 3 here, right? This way on the outside, the product is 10, and on the inside it's 3. And you can't make 7 out of that by making the 10 positive and the 3 negative. So it's like that, right? This is a somewhat hard factoring. I hope that at some point you learned how to do that. Anyway, let's proceed from there. What was I doing is finding the critical numbers. So this is set equal to 0. I just factored it. That means I just set each part equals 0. That 2 in the front doesn't matter. Solve for x. I get x equals a half, and here x equals negative 5/3. Right? These are my 2 critical numbers. This can be a little confusing when you're doing the second derivative test. I don't know if anybody was immediately confused. I said use the second derivative test, but everything I've done so far has been using the first derivative. That's because the second derivative test involves the critical numbers, and those come from the first derivative. So just because I said second derivative test doesn't mean that you only use the second derivative. Remember the strategy, though, is this right here. You take your critical number and you plug it directly into the second derivative and you test if that's positive or negative. So that's what I'm going to do next. I'm going to plug, these are my 2 critical numbers. Plug these into f double prime and see if I got positive or negative. And that's how you tell if it's a minimum or a maximum. If you get a positive, it's a minimum. Negative, it's a maximum. Now, we actually never found f double prime, not yet, at least in this problem, so I have to, starting here, take the derivative again. That's what f double prime will be. So it's going to be f double prime of x is, you still see it up there? There it is. 24x plus 14, right? That's the second derivative. And then what I said I'm going to do, plug those two critical numbers into the second derivative. So the first one, f double prime of 1/2 shall be 24 times 1/2 plus 14. This is 12 plus 14, which is positive. All right, so f double prime of 1/2 is positive, so x equal 1/2 is a local, was it max or min? I heard, see what you're doing there. What is it? Say it louder. Minimum, yes, thank you. If you get a positive, that means the shape is like this, which means your point is a minimum. All right, what about the other one? F double prime of negative 5/3 equals 24 times negative 5/3 plus 14. This 24 times negative 5/3, if I do 24 over 3 is 8. So this is really 8 times negative 5 plus 14. That's negative 40 plus 14, which is still negative. So x equal minus 5/3 is a local maximum, because I got a negative there. All right? And this is how we do the second derivative test. I don't need to go through the details, but let's just think briefly about, is this better or worse than the first derivative test? The answer is, I think in this particular example, this was a little easier. If I had asked you to do the first derivative test instead, you still had to do this stuff to find the critical numbers. In the first derivative test, you then would have made a chart, marked these things off, chosen 3 values to plug into the first derivative. And then based on the signs, you'd say up and then down, or down and then up, all right? That's the first derivative test. Instead of doing that stuff with the chart, we just plugged these numbers in and immediately said, this is a minimum, this is a maximum. It's not a whole lot easier, but I would say in this example, maybe the second derivative test is a little bit more straightforward. All right? Great. I got one more, and then I think maybe that'll, well, we can probably say a little bit more than just one more example. Sorry to play with your emotions like that. This example is not going to take 20 minutes. Let's try another one. How about f of x equals x plus 4 over x squared? Same thing. I want to use the second derivative test to identify any local extrema, local minimum or local maximum points. All right. Remember, we begin, so the large-scale strategy is first find the critical numbers using the first derivative, and then plug those numbers into the second derivative. So let's start by finding the critical numbers. You've got to take the derivative. How should I handle 4 over x squared when I do the derivative? Yeah? Yeah, rewrite this as x plus 4x to the minus 2, and then take the derivative like that. So f prime of x is just going to be 1 minus 8x to the negative 3, right? And just because we're here, would you mind if I take the second derivative also? We're going to use that eventually, not at the beginning, but the second derivative, the 1 will go away, and then this part is going to be 24x to the minus 4, right? All right, we're not going to use the second derivative immediately, but we will eventually. Okay, what should we do for the critical numbers, right? We have to use the first derivative and set it equal to 0, and also say when the first derivative does not exist, right? Let's do the equals 0 part first. It says 1 minus 8x to the minus 3 equals 0. when you're trying to do the algebra steps to solve for x, if you see negative exponent, it's a good idea to write it out as a fraction. That will help you tell what the appropriate algebra steps are. So this really, as a fraction, looks like this. And now I think the way I would solve that is add that little fraction over the right side. 1 equals 8 over x cubed. And then maybe multiply both sides by x cubed to get rid of the denominator. X cubed equals 8. X equals 2, right? Is it plus or minus 2? Or just plus 2? The answer is no, it's just plus 2. Because minus 2, when you cube it, you get minus 8. So we don't want that. It's only 2 when you cube it, you get 8. All right, so x equals 2 is a critical number. What about, we should also check when f prime does not exist. This is only important when there are denominators on the scene, but actually I think there are denominators in this case. The first derivative was 1 minus 8 over x cubed, writing it again as a fraction, right? So what's my critical number from this step? What value of x makes the denominator 0? The answer is 0. They're giving me the hand signal again. All right, great. Okay, these are the two critical numbers. To finish off, we have to plug these into the second derivative and see what happens. Actually, there's a little technicality here. In this problem, getting 0 in the DNE step is no surprise at all because the original function also does not exist when x equals 0. Actually, this is a vertical asymptote for this function. So I'm going to say for this one, the original function, f of x, does not exist when x equals 0, right? When, it looks like I wrote when x equals 0. The original function would have an x in the denominator, right? So the original function f of x does not exist when x equals 0. That means actually this is kind of a red herring. This is not a local minimum or a maximum because there's no function there at all. Right? There's no point at all. So here, f of x does not exist when x equals 0. So that means x equals 0 is not a minimum or a maximum. You might fool yourself if you plug that into the second derivative. Although, if you did, you would have got a DNE anyway, because this would give you a 0 in the denominator also. You would have been puzzled, right? Anyway, the 2 will give us something legitimate. So I'm going to do f double prime of 2, right? What is that? You remember your formula for f double prime was 24, right here, 24x to the negative 4 power. So this is 24 times 2 to the negative 4. And is that positive or negative? 2 to the negative 4 power. No? I think it is positive. Isn't it negative because of the negative exponent? No. Yeah, right. The negative exponent doesn't make the answer negative. It makes the answer in a denominator. So this, if you were to write it out in more detail, this would be 24 over 2 to the 4th power. And that's positive, right? There's no actual negative numbers involved in that. So that means x equals 2 is a local min, right? When you get a positive from the second derivative, that means it's a minimum. That's that. Local minimum. All right, this is the second derivative test. Like I say, I meant to do that before, but I'm doing now. All right, it is another method for deciding whether something is a minimum or a maximum, rather than making those charts with the increasing decreasing. Anybody got thoughts about that? Questions? All right, we got 13 minutes remaining. That's enough time to start talking about the next section. I think probably everything I say in the next 13 minutes will be fairly ordinary sort of common sense introduction to the next bit. This is still on the general theme of graphs and sort of like what the graph looks like, although at least temporarily we're not going to be talking about the derivative much in this little section. I want to talk about horizontal asymptotes. horizontal asymptotes, all right? These, I hope everybody knows what that means. On a graph, this is also known as limits at infinity. Limits at infinity, all right? Those are sort of synonyms. Horizontal asymptote is kind of a synonym to limit at infinity. I'm going to try and connect the dots about why those two phrases are the same. For example, a function like, here's a function 2x over x minus 3, all right? And it looks like, you can check this on your calculator if you want, it has a vertical asymptote here at x equals 3. That is caused by this denominator becoming 0 when x is 3. When the denominator becomes 0, that causes a vertical asymptote in the picture. There's also, this function also has a horizontal asymptote at y equals 2. So this is at 3. This here is at 2. This 2, it's not a coincidence that that number right there is 2, although you can't always just pick out this number and say that's where the horizontal asymptote is. But anyway, the rest of the function looks like this. It's like one of those. It basically looks like 1 over x, but shifted and stretched. All right. So this one right here is a horizontal asymptote. Whereas this one is a vertical asymptote. I went on somebody's calculus test, they wrote it like this. Vert-ass, which I thought was funny. Sounds like something that means something. It means vertical asymptote, obviously. Yeah. That's a vert-ass. So we are going to talk mostly in this section about horizontal asymptotes. The vertical asymptotes are easy to find just because they occur when the denominator equals 0, and we already know how to figure that out. The horizontal asymptote is a little more interesting to find. The horizontal asymptote, so can I just say in a little bit more language what I mean when I say that's a horizontal asymptote? What I mean is when the x value goes off to the right, the y value approaches this line. Actually, the y value approaches the number 2, right? So what is meant by horizontal asymptote? It means as x increases forever, f of x approaches 2, right? In this example, the y value approaches 2 when the x goes off the page to the right, all right? Another way of writing this, so this business right here, sorry, I'm sort of out of room. I'm going to come back down here. This can also be written like, actually, when I say what those little words inside the box there, I said approaching. It kind of sounds like I'm talking about a limit of something. And the only sensible way to write this as a limit, as x increases forever, the way to write that as a limit is like this. The limit as x goes to infinity. That's what I mean when I say as x increases forever. And in this case, it's the limit of that function, right? 2x over x minus 3. And what I said, it approaches 2. So that's what the answer to that limit is, all right? And this is what we mean when I said, like at the very beginning, this is called a limit at infinity. At infinity means, there's an infinity down here, right? That's what it means when somebody says a limit at infinity. It means when x is approaching infinity. And what that means is when x just gets really, really super big, goes off to the right forever on the graph. The y value in this example approaches 2, all right? And you can also talk about the limit as x approaches negative infinity. That would mean the limit when the x goes off the other side, to the left. Your left. So that would be lim x goes to minus infinity of 2x over x minus 3. That means, look on the graph, what does the y value approach when you go off the side to the left? In this particular example, it also approaches 2, right? But in general, those two, sort of the asymptote going off to the right might be different from the asymptote going off to the left. That's possible, and we have an example like that. We're not going to get to it today, but anyway, this is also equal to 2, all right? And this is called the limit at minus infinity, all right? As x approaches minus infinity, that means x becomes super negative, goes off the graph on the left side, all right? These are called limits at infinity, all right? This is different from, I'll put sort of a parenthetical here, different from infinite limit. We did talk a long time ago about infinite limits. That phrase refers to something like this: lim x goes to 0 of 1 over x squared equals infinity. When you see the infinity over there, that's called an infinite limit, because in this case, the limit actually is infinity. The limit is infinite. So this means the limit is infinite. This is different from the limit at infinity. That means the x is approaching infinity. When you say the limit is infinite, it means the limit actually equals infinity. So very similar phrases, but they mean really totally different things. Or you might say this indicates a vertical asymptote, right? 1 over x squared, the function looks like this. So when I say this limit equals infinity, it means as the x is close to 0, the y values go up forever, which is different from a horizontal asymptote. I mean, different from a limit at infinity. That's horizontal asymptote. All right? And let me just tell you, in our remaining 6 minutes, basic facts. I will tell you 3 basic facts about limits at infinity. It won't take 6 minutes. Basic fact about limits at infinity. This is not complicated at all. This is the most basic of the basic facts. Limit as x goes to infinity of 1 over x. I think everybody knows this. You have to imagine, if I have a fraction like 1 over x, but the denominator is becoming super, super infinitely big, what is the limit going to be? Yeah? 0, yes. If you can imagine a fraction where the denominator is increasing forever, the value of that fraction gets smaller and smaller, and when you actually do the limit, you get 0, all right? This is because the denominator is getting super small. In fact, that was the first of the basic facts. In fact, just to be a little bit more specific, it's also true, this is true, even if I put some other constant on top, you're still going to get 0, right? Even if it's, 3 divided by x. When you let the denominator become infinitely big, you're always going to get 0, no matter what the constant is. And I'm also going to add a little, even if you put a little exponent in there, you're still going to get 0, as long as the r is greater than 0. If the r was a negative exponent there, then actually this would flip the fraction upside down again, and then the x would be on the top, and it wouldn't be 0 anymore. But as long as the r is not a negative exponent, any constant divided by some ordinary, like, positive power of x, you're always going to get 0 when you do that limit. And what if you let x go to negative infinity? The answer is this also is going to be 0. So this means you let the bottom, the denominator, again, will become sort of infinitely large, also equals 0. I'm going to say if r is a positive integer here, some weird things will happen. If you let r be a fraction, for instance, r equals 1/2, and then use negative numbers, this would give you square roots of negative numbers, which mess the whole thing up. But if r is an ordinary positive integer, then this works out just fine. So the moral of the story is basically, if you have a power of x in the bottom, you're going to get 0 when you do the limit at infinity, or the limit at minus infinity. You get 0 either way. All right? And I think that'll do it. This was basic fact. We're going to turn this into more interesting things next time. I hope you have